Yeah. So now the presentation is recorded and my voice is recorded. So I will upload the presentation, including the recordings, after the well, somewhere today probably. We'll put out a tweet on to Amsterdam Data Science so you can find my presentation. First about myself, thank you for this introduction, Nanda. Who am I? I am Jurjen Helmus. I'm a father, so most days I'm tired. I'm an old-timer lover living in Amersfoort. I'm the coordinator of the minor data science at the University of Applied Sciences. We just had our first application for students to apply for the science, the minor, and within 28 minutes we had 78 applications. So data science is not only on the university very popular, but also at the HBO's in the Netherlands. And I'm conducting my PhD research at the Computational Science Lab of the UvA on charging infrastructure and social supply-demand systems. And I'm going to tell you today something about our research. I first give you an introduction in the EDOLAT program. The EDOLAT program is at the University of Applied Sciences, where we collect data from all the charging infrastructure in the Netherlands. And charging infrastructure is very important for several reasons. First, by the EU regulations, we need clean air in the Netherlands, and we need clean air policies. And for example, the municipality of Amsterdam stated that they want to have an emission-free city center in 2025. That's 7 years from now. There will be no vehicles allowed with internal combustion engines in the Netherlands, in the city center. And why is this important? Because, as you can see here, these red dots are all the dots with air quality below the standards of the European regulations. So this is really a problem for the city of Amsterdam. We are one of the front runners in the world. And why is the city of Amsterdam such an important city? Well, because we have a charging infrastructure density, particularly in the Amsterdam South area, which has charging stations within walking distance of 2 minutes from here to your next charging pole. We have the first worldwide electric vehicle car sharing scheme, first deployed electric taxis and subsidy schemes for entrepreneurs. But there's a lot of problems with these and challenges for municipalities for deploying charging infrastructure. First, of course, it's very costly, and it has to be used by EV owners to make a business case. The EDOLAT program supports policymakers, and our research focus on it's apparently automatically skipping, so I'm sorry for that. Yeah. 3 pillars within the EDOLAT program, how we support these policymakers. First of all, we do monitoring of the performance of this charging infrastructure. So we collect all the data of the charging infrastructure and we define KPIs and key result indicators to help policymakers to make better decisions on deployment of charging infrastructure. This is like business analytics. Next, we make predictive analytics. We predict how charging infrastructure and how the occupancy and availability of charging infrastructure will behave in the upcoming weeks in the near future. And the third pillar is modeling and simulation. We also make future scenarios, how to deploy for a future that's fully emission-free. For example, the city center in the Amsterdam area. We have a unique data set, as Nanda mentioned. We have 77.5 million records of users from the charging infrastructure in the Netherlands. Yeah, skipping again. From about 100,000 users and 7K charging stations from all large municipalities in the Netherlands. So Rotterdam, The Hague, Utrecht and Amsterdam. The metropolitan area as well. And we get specific information from, for example, taxis, car-to-goes, entrepreneurs about the charging cards to specify and identify specific user types to roll out charging infrastructure specifically for these users that demand different profiles for availability. We use contextual data, open data, parking data, and pricing data. And we collect data monthly, but also almost real time by a REST API that sends data from the charging infrastructure directly to one of our servers. Of course, it's all behind a firewall and not available publicly because for privacy reasons. So don't worry, we don't know who you are and where you are at this moment. So we know for every user that has charged on which charging points, the RFID numbers, the locations, and the transaction size. And the transaction size, of course, in energy is important to, for example, make grid predictions and check whether the grid can occupy and accommodate for the needed electricity for electric vehicles. Three main pillars within our research. First is we do about network models, so we make network models for the grid and for the charging infrastructure. We make agent-based models for EV, so in Python we created a simulation model for charging behavior of electric vehicle users to check on future scenarios. And the last thing we do is make a microscopic traffic model. You all might know the Amsterdam traffic model, which calculates flows of traffic. We imported a model from Singapore that is able to simulate individual users with individual vehicles in a city center to check what happens if you make an emission-free city center. This runs on Serve Lisa, and in 1 month we spent 750,000 CPU hours for simulations. We got quite an email from Serve. Could you please put down your requested CPU hours, because there are others on the server as well. But in the end, we are able to identify weaknesses and policies that are required to make our city emission free. Today I'm going to tell you something about the network models. The network, so the charging infrastructure, as you can see here, this is the city of Amsterdam, and these are all charging spots. So these are all charging spots in the city of Amsterdam, and the green lines indicate that there's a relevant walking distance between one and other charging stations. So for example here you see that if I'm here, I have an alternative charging station there and there to use if my charging station is occupied. So the system can be seen as a network, as a bipartite network of supply and demand for resources. Just like other networks, for example, foraging animals, in this case it's charging infrastructure. And from the network idea, we can say, okay, what happens if we tweak the network, if we play around with the network density, or help to increase density or remove unneeded charging points. So what you typically see in these network properties is, for example, cascading failures of networks. So if one node fails, other nodes might fail as well. And we're talking about network robustness. So how can we make a network that's robust, that's able to accommodate for disturbances? And disturbances can be, in this case, visitors or non-working charging points or electricity failures. And from this we can, based on the data, without simulating, we can check how the vulnerability of the network behaves. So from this walking distance idea, we create a network, and from the network we are able to simulate what happens if one of the charging points fails. So in this case we have a relevant walking distance varying from 400 to 600 meters. This is a charging station, and these are the areas with the relevant alternatives for a user. Now, cascading failures, yeah?
You're driving a car and you're talking about walking distance.
Yeah. So it's confusing. Okay. So there are 5,000 charging stations in the city of Amsterdam. You want to charge your car, you come back home or in your office, and in this case your charging station is occupied. Can happen. Then what? You want to charge your car. So because you're somewhere in the area of your charging station which you mostly preferred, you wonder, okay, which relevant alternative is there in my neighborhood to drive to this alternative and then walk probably to the area around the charging station that you mostly prefer. So this relevant walking distance is about, okay, what if something fails, is there an alternative that I can reach by walking?
So it's the last mile problem.
It's,
From your car to your home or your
yeah,
destination.
this kind of the last mile problem, and this last mile problem is very important because if you're in this area, yeah, then there is no last mile. But if you see here in this area, there's a lot of opportunities for you to search for an alternative.
Also expand double the infrastructure.
Well, that's the question. The question of policymakers is how to roll out this charging station infrastructure efficiently. And efficiently, in this case, means that it's used and it's not too many rollout of charge oversized. Yeah, so the charging infrastructure is very, very costly. So indeed, you can increase the number of sockets, but then you get the problem that if you connect multiple cars to the same grid connection, then the electricity grid fails. So in this case, it can happen that you say, okay, we roll out more sockets in the neighborhood, in the same charging point, but it's not necessarily the solution. So what we do is we, in this simulation in this data-driven analysis, is we create cascading failures. So what we do, and cascading failures is typically a few weeks ago we saw a cascading failure in the network of electricity network in Amsterdam. One firework here, caused all the trams in the city center to stop. And you can imagine that if the charging infrastructure is very highly occupied on certain time schemes, then if there's a disturbance in the system, like for example a visitor on a charging station that's normally occupied by you, then you have to divert to a different location. Having you divert to a different location could mean that the mostly used user of the alternative has to divert as well. So we get cascading failures in the system due to the fact that people aren't able to use their mostly preferred charging station. So what we did is we took the data, we created a network, and we removed one at a time a charging station. So we removed the charging station, and for all the sessions at these charging stations, we looked whether there's a relevant alternative for this charging station in the neighborhood. Are there relevant alternatives? Okay, yeah. Does this charging station, which is a relevant alternative within the walking distance of the other charging station, does it fit? Is it occupied or not? So we looked at the data of this charging station, whether the session fits. If the session fits, fully fits, then there's no problem. If the session fits but pushes out a new user on this alternative charging station, we got an iteration. So there's an alternative, but if it pushes out a new user, you got back to this question. Okay, is there an alternative charging station for this user that's pushed out, and can we redo the analysis? Yeah.
Is the network the physical electrical connection or your abstract?
The network is the network of relevant alternatives, like you've seen here.
And like what are the connections over there?
So the connections are the walking distances between the charging stations. Yeah. So here you get, of course, a very dense area because the charging stations are very densely distributed across the city of Amsterdam. But here there's no connection between other charging stations because there's no walking. So the network has a degree of 0 in this case. Yeah.
How many charging stations in Amsterdam here? 500,000?
What?
How many charging stations?
5,000.
5,000.
Yeah. 5,000 charging stations, 7.5 million records of sessions.
On that same question, those are all the public charging stations?
We all do public charging stations.
No? So anything that's in businesses and so, do you have any idea what fraction of the total
Yeah.
charging
The point is, in the city of Amsterdam, charging is mostly public charging because no one has a real own driving lane, except for offices indeed. And we we are, because this is, the questions is very relevant for policymakers to, in areas which have residential zones combined with office zones, it could be beneficial to open up the private garages of the companies for residential charging as well. So in this case, we only look at public charging infrastructure publicly available in the public space. But there's a part of our research that now collecting the private or the owned charging stations to look how the system would accommodate for more users in combination with offices. Yeah, that's a good point. We're looking at this as well. In this case, we're only looking at the public charging stations. And one of the things that's very important in this area, in the city of Amsterdam, is that in this dense area, we have this car sharing scheme, Car2Go, which is noise in the system. But we also have a lot of visitors visiting Amsterdam, putting their electric vehicle in the evening in a residential zone nearby a point of interest. And you get a lot of disturbances due to uninhabitable users. So the question here is, can we accommodate the system, particularly in this area, for the habitual users that have a habitual pattern for using the charging infrastructure? Yeah. So the simulation. So this was the simulation. So we simulated for all the data. This takes a while, but we are able to really check on the accommodation of the system. Now, we defined two types of failures in this case. We defined service failure, and service failure means that the system cannot accommodate for the charging sessions of a user. This can be either a first order problem that there's no alternative in the neighborhood of a failed charging station or an occupied charging station, but it could also be somewhere in a cascade. It could be and a cascade and a service failure. So you push out all the users and there's some user in the end that cannot accommodate, cannot charge, and then the system cannot accommodate. So what you see here is that the service failure is mostly in the outskirts of the city where the network is dense, which is, well, what you would expect. Now here, this is a picture of the inconvenience. And the inconvenience we define as how many users need to divert to an alternative location if one location fails. I don't know that by. You have it's growing massively, and what you see is the ratio between. So in the beginning, in the first phase of rollout, we're talking about 2013, 14. You had a ratio of one charging point with 2 sockets for one user. But what you now see is due to the second order growth effect that users don't apply for a charging station but do buy an electric vehicle. So you get a ratio that's not 1-to-1, not 2-to-1, but even higher. So there is, particularly in the city center, and there's very BNR radio and on YouTube, look up occupied charging stations. You see movies of people with their dash cam traveling around in the city center of Amsterdam, being annoyed because all charging stations are occupied. So it's really a real problem. And the problem is real from the point of disturbances from high occupancy, but also failed connections. So really the charging stations themselves fail. So there's a threefold problem that's visualized here in this data set. I've seen you nodding yes, yes, yes. You have experience with what you see here is the city center, of course, and the red dots indicate a vulnerability of score of 10. So if one charging station fails, 10 other charging stations fail as well. Meaning this, on 10 other charging stations, you have a cascade of users times 2 sockets of 20 users that need to be diverted to other charging stations. Well, that's a lot. Particularly in areas with visitors that are able to unpredictably present in the system. So this is for the policymakers a very important figure to check on how to roll out charging infrastructure not only for users but also for convenience.
Do we have an, sorry, can I ask a question?
Yeah.
Do we have a clue about if you improve
make them work more often,
Yeah.
how this impacts?
Yeah, that's a good question. That's part of my PhD. So I'll send you an invite in 2 years. One of the last things I want to mention, we, as a University of Applied Sciences, we do, in my case, I'm partly doing fundamental research, but also applied research. So these research are implemented in our Shiny server tool available for the policymakers, and they now have the availability of this Shiny tool to roll out charging infrastructure in such a way that you can see how the vulnerability per month is, and to roll out in specifically for improving network convenience. What you see here is the year, the month, the relevant walking distance, what kind of failure do you want to see, what values, and you here see the values of each charging station in Amsterdam. So there's a lot of charging stations with the vulnerability values. So you can really look up for each month how the system behaved in a specific month and where to roll out new charging infrastructure given that you want to have a convenient system.
So you want to roll out close to the red dots?
Yeah, you want to roll out close to red dot in such a way that if I put, for example, here in the middle a charging station, then it's a relevant alternative for 1, 2, 3, 4 other charging stations. So you increase network density, and by increasing network density, you get scaling effects of the network.
But what I notice here is that the low density is also where the low income, that people don't have a lot of electric cars.
Yeah.
Being the outskirts. So that means also there's low high fidelity because the walking distance is not there.
Now this is a very fun fact.
Yeah.
These are all Tesla taxis.
Okay. So it's the people,
Yeah.
Okay.
So this is where demographic data doesn't fit the regression models. Yeah. These are all the Tesla taxis.
Just good segmentation.
Yeah.
That's bad for business.
Yeah, indeed. Here it's very bad for business. First takeaway. Data science is not only about machine learning. I speak to a lot of people in the business field, and they, particularly in consulting, and they say, we come in, we draw a neural network, and we leave the company with a very quick and a good implementation. It's also about information science, like information theory and network theory. And that's the first thing is broaden your scope and don't focus only on the neural network part. The second part is the measurement problem. What's not in the data is not measured. We created a tool here with our project that's able to measure things that are not directly in the data. The vulnerability itself isn't measured. You simulate it according to the data, and from there you draw conclusions. Last takeaway, keep track on what your end client needs. We created this Shiny dashboard that's available for our end users that are able to make decisions based on the results of your data science project. We could have done it in a fundamental way and define metrics that are maybe fundamentally better, but in this way, by focusing on the inconvenience, we are able to really support the policymakers with our toolings. Questions? Coffee?
Okay, well, thanks.
Yeah.
We have time for one quick question. I see three, so we can do three quick questions. 4 or 5? Ian.
Yeah, thanks. How generalizable is your model? I mean, I've seen how it might work, like in Amsterdam, but for instance, have to check if it really works in other cities or maybe cities across the world.
Yeah, good question. The model is generalizable not only on a city scale, like we make the model for the G4 cities, so Amsterdam, Rotterdam, The Hague, and Utrecht, and the smaller cities like Haarlem, and it works quite well there. It's also, and that's what my thesis is about, it's generalizable in other types of systems. We're talking about social demand supply systems. You could even use it in the savannah for foraging animals. So you take the speed of transferring food, location of food, and if a location fails, for example, a mud pool or an oasis, then you have a cascading failure in the ecosystem.